So hi everybody, welcome back. For this lesson we're going to be working on separable equations. And I want to start off by defining what a separable differential equation is. And this is a function that can be expressed as a product as a function of x and a function of y. In other words, if we take the function that we're looking at, or this differential equation that we're looking at, can we factor it into a product of all of your x values, which will be condensed into one function, and separately all of the y values, which will be condensed into a separate function? If we can do so, then this is a separable differential equation. Now, we want to get a separable differential equation because it will help us solve for y. If we have a differential equation, that means we took a derivative for some function of y with respect to x, and we were looking at g of x times h of y. Now again, we got to keep this in mind. We could have possibly done this implicitly in order to get a variable y or a variable y prime in the mix for this differential equation. Nonetheless, when we get this differential equation that is separable, in order to separate it, we must be able to multiply or divide by the respective functions, either the x functions or the functions containing the y values. When we do so, we now have these differentials that we can work with. And these differentials will help us identify which functions we need to integrate with respect to y and with respect to x. Because at the end of the day, we will be able to solve for the function of y if we start looking at the integral for the function that contains y. Once we get that function, then we go through our algebra techniques and we can solve for y. So, let's give this a shot. Let's look at part A. Part A, we want to solve the differential equation. And again, this differential equation will be separable. In other words, can we then identify one factor that is containing only x's, and can we identify another factor that will only contain y's? If we can, then the product of those two will get us the differential equation here. And in this particular case, we can then separate the differential to say that we have dy is equal to x times the square root of y dx. Notice, my differential for dx is on the right-hand side. Naturally, I want to keep my variables for x on that right-hand side. So in order to move my variable of the square root of y to the other side of the equation, I'm going to divide. Now, I get y to the power of negative 1/2, and again, because we're dividing, dy is equal to x dx. Now, one way that you might see this a little bit better is if we had y to the power of 1/2 initially, and then we divide by it, which means the denominator is now y to the power of 1/2, which means it's a negative exponent. So once we have this portion split, or in this case separated, to their respective variables on their sides, we then integrate. The integral of y to the power of negative 1/2 with respect to dy is equal to the integral of x dx. Now, we go ahead and we integrate. On the left-hand side, we're integrating with respect to y, which means we add 1 to the exponent, so we get y to the power of 1/2, and we divide by that new exponent, which means we'll multiply by 2. This is going to equal to the right-hand side, where I'm going to integrate with respect to x, which will now get me 1/2 x to the power of 2. And again, since both of these are they're both indefinite integrals, I need a constant. Once I have this, I can then start solving for y. Y is going to, y to the power of 1/2 is going to be equal, multiplied by 2, and this will be x squared plus, we can say 2c, that'll be okay. Alright, good so far? Let's keep going. In order to solve, we square both sides. So I'm going to square both sides. Oops, excuse me, not y squared. I square both sides to now get me x squared plus 2c to the power of 2. Great. Now at this point in time we can replace a constant here, because notice we have 2 times a constant. Well, 2 times a constant is just going to be another constant itself. So what I want to do in this particular case is I just want to denote that we have one constant. So y, or a singular constant with no terms or no coefficients in the front of that constant. So we have x squared plus, in this case, let's pick a different variable other than x or c. And let's go with k. And this is going to be where k is equal to 2c. Alright, not too bad. Alright, now, this could have happened, let's say, a little bit differently if we had to evaluate these integrals in more of a definite sense. Okay, but again, we'll keep that in mind as we keep going through. And I just realized I made a mistake. Crappers. It's a late night. It's okay. It's okay. So I'll make my corrections in red. So dividing by 2, I get 1/2 here, but 1/2 divided by 2, that's going to be 1/4. And then my constant for c, it's not going to be 2c, it's going to be c divided by 2. There we are. Now again, making my corrections, 1/4 x squared plus c over 2. And again, I'm still going to replace that constant, 1/4 x squared, but now my k constant is going to be c over 2. And there we are. So again, my apologies there, but we now have the correct solution on screen. Great. So let's go ahead and let's give the second one a shot. Let's go with part B. And so again, this is my solution. So going over to part B. In part B, we have that the differential dz divided by dt, or dz dt, is going to be added. So again, we're talking about adding here. E to the power of t plus z is equal to 0. Well, what we can do here is we can do dz dt is equal to negative e to the power of t plus z. Okay, pretty good so far. All I did was subtract e to the power of t plus z to both sides. Now what I can do is I can talk about separating this differential equation. So how in the world will we separate this? Well, we can separate this by recalling that anytime that we have a base and in that exponent for that base we have an addition, then we can separate using addition. Or sorry, we can separate using multiplication of the base. Therefore, we have now separated, and all I need to do now is isolate my variables on one side, or isolate my respective variables on one side. Notice the dz variable or the dz differentials on the left-hand side, so I want to keep all of my variables for z on the left-hand side. So I'm going to divide by e over z. So this is going to be e to the power of negative z dz is equal to negative e to the t dt. And then we integrate. Looking pretty good so far. Let's keep it going. All right, so on the left-hand side, we're going to integrate, and integrating on the left-hand side, we're going to get negative e to the negative z. On the right-hand side, we integrate, and we get negative e to the power of t plus my constant, which we'll call c. Okay, let's keep going. Again, we're trying to solve here. Typically, you want to solve for your variable or for your function that you initially took the derivative for. In this particular case, since the differential is dz dt, we want to solve for z. So solving for z here, I'm going to divide by a negative or multiply by a negative on both sides. Oops. Which will leave me e to the t minus c. Take the natural log of both sides. Then we get the natural log of e to the power of t minus c. And then divide by negative. So we now get that z is equal to negative natural log of e to the power of t minus c. And there's your final answer. That's it. We have nothing else for that answer. And we are done with that question. Okay, looking pretty good so far. This is the way differential equations operates. Now, once you get into that course for differential equations, you will expect to be doing this more frequently and at a larger or a more heftier intensity. So what I want you to do now is I want you to take some time and read this equation or read this prompt for this question. And the prompt says that we need to find the solution of the differential equation that satisfies the given initial condition. So the given initial condition here is that y of 0 is going to be equal to 1. And the differential equation is the differential equation that is given to us, which is x plus 3y squared times the square root of the quantity of x squared plus 1 multiplied by the differential dy dx. All of that is equal to 0. That's a differential equation we want to solve. All right, so let's get to it. We want to solve this differential equation, so what we're going to do is we're going to try to see if it's separable. And chances are, because we are in this section of separable differential equations, it will be separable. So what I want to do is I want to try to start isolating my differential. And that's going to be my overall goal here at all times. So let's isolate that differential times dy dx is equal to negative x. Okay, looking pretty good so far. Now, at this point in time, I'm going to multiply by my differential dx. This way, I can have my dy's being on kind of on one side for now. That's negative x dx. And as we can see, we're already starting to isolate all of my y variables in that differential. So the natural last step will just be to divide by the square root of x squared plus 1 on both sides. And this now gets me on my right hand side negative x divided by the square root of x squared plus 1 dx. This is great now because now I can take my integral. So taking the integral of 3y squared dy and the integral of negative x over the square root of x squared plus 1 dx, well, on the left-hand side, we're just left with y to the power of 3. Okay, so that's not too bad. On the right-hand side, it's a little bit more convoluted. So on the right-hand side, if we say u is equal to x squared plus 1, then du is going to be equal to 2x dx, which means that x dx is 1/2 du. Okay, that's not too bad. We have the negative, so I'll keep the negative out in the front of the integral. Now, I have 1 over the square root of u, which means this is u to the power of negative 1/2, and my dx here, my x dx, is going to be 1/2 du. So that's 1/2 du. Let's keep going. This is still y cubed, negative integral, and actually I'll factor out the 1/2, so negative 1/2 integral times u to the power of negative 1/2 du. Now we can go ahead and integrate u, and integrating u, what we're going to do is we're going to add 1 to the exponent, so that's going to be negative 1/2 plus 1, which is 1/2, and then we divide by that exponent, or sorry, we divide by that new exponent, which will be dividing by 1/2. In other words, we're multiplying by 2, so we then just get negative u to the power of 1/2 plus c. Now that's looking pretty good so far. It's looking promising. So I'm going to remake my substitution because, again, I'm not trying to solve for u. I'm trying to solve for whatever x variable I had in there. So this is now going to be y to the power of 3 is equal to negative quantity of u, where u was this x squared plus 1 to the power of 1/2. And then I have my plus c. Okay, looking pretty good so far. I like this. Okay, let's keep going. Now what I'm going to do is I'm actually going to use my initial condition. So I'm going to say use the initial condition. The initial condition says that my x values are zeros and that my outputs, in other words, my y values, are going to be 1. In that instance, I get that 1 to the power of 3 is equal to negative quantity of 0 to the power of 2 plus 1 to the power of 1/2 plus c. This tells me that my c value is going to be, well, in this case, c is going to be 2. Why is it 2? Well, we can go through the whole calculation here. We get that c is equal to 2. There we are. All right, not too bad. So we then get that c is equal to 2. So let's go ahead and let's make that substitution now. Or let's make that value that we found plugged in. This is x squared plus 1, square root of x squared plus 1, and then that c value was plus 2. So that's plus 2. Now all I need to do is solve for y. Well, solving for y, that just means I need to take the cube root of both sides. And that's going to be 2 minus the square root of x squared plus 1 raised to the power of 1/3. And here is our solution to that differential equation. Nice, simple, concise. That's it. All right, so this is how we use, or this is how we set up these differential equations. That way we can use the integration and the differentiation techniques that we have learned throughout all of our calculus classes. So let's look at one more question before we wrap up this section. So the very last question that I want to look at here is going to be this question. This question says that a tank contains 1,000 liters of pure water. then brine that contains 0.05 kilograms of salt per liter of water enters the tank at a rate of 5 liters per minute. Brine that contains 0.04 kilograms of salt per liter of water enters the tank at a rate of 10 liters per minute. The solution is kept thoroughly mixed and drains from the tank at a rate of 15 liters per minute. So the question then becomes, how much salt is in the tank? Part A, after t minutes. In other words, let's get that differential equation going. And then part B, how much is left after 1 hour? Okay, so here's where we now need to start looking at this particular problem in terms of a differential equation. So let's go ahead and let's start defining what it is that we want to look at. Now, again, they're giving us a rate. They're saying water is going to enter the tank at a certain rate. Brine is going to enter at a certain rate. Brine enters at a certain rate, 5 liters per minute. Then a different type of brine is going to enter at another rate, 10 liters per minute. And then it's going to drain out of the tank at a rate of 15 liters per minute. So what we then want to do is we want to then analyze that since we're given these rates, that's what we want to work with. So I'm going to identify here that they're telling us, hey, you're working with a rate and this is going to enter. You're working with another rate and that's going to enter as well. And then you're going to drain at a certain rate. All of these rates will then signify to us that we have some sort of differential equation. So we then want to look at dy dt in terms of the rates that we're looking at. In other words, what is the rate in and what is the rate out? Now, in this particular case, we then want to identify that the rate is going to be the change in the amount of brine that is in here. Or in this case, brine contains a salt solution. Therefore, it's going to contain the change in the salt. The change in salt that we are looking at here. Okay, so we're going to just make sure we word that here. So I'm going to denote it here that dy dt is the rate of change of the amount of salt. Now, this is going to be beneficial then, because if dy dt is the rate of change of the amount of salt, then naturally when I take the antiderivative, I should only be left with the amount of salt that we have, or the amount of pure water that we're going to be looking at. All right, so that's kind of what we want to keep in our minds. Now, let's start looking at the different rates that we have here that we're going to be observing. Okay, so here we go. Now, my rate in, that's going to be what I want to focus on first. So this rate in. So that rate in and again, I want my rate to be in terms of the change of amount of salt. Okay, so let's go ahead and let's start extracting that. First of all, the first brine that I'm looking at, the first brine contains 0.05 kilograms of salt per liter of water. Okay, so that's going to be my first rate that I'm looking at. That 0.05, and in this particular case, we get kilograms of salt, so kilograms of salt per every liter. Now again, if I want that rate in versus rate out, what I'm going to do is I'm going to say, okay, well this rate is coming in at 5 liters per minute. So at 5 liters per minute. So notice that when I multiply these two quantities, the liter amounts will cancel, and we're going to be left with how many kilograms of salt per minute this certain brine is going to be producing. Okay, but I don't have that brine itself coming in. There's a different type of brine coming in. That brine that's coming in as well is 0.04 kilograms of salt per liter, and that's going to enter at a rate of 10 liters per minute. Now again, once I multiply these two quantities, well then naturally we will be left with kilograms per minute. And again, that is then going to give us the amount of salt that is going to remain in that tank, or at least the rate of change for that salt in that tank. Now we need the rate out. So let's go find the rate out. Okay, so for the rate out, again, the solution is going to be draining. It's going to be mixed and it's going to be draining. At this point in time, we have no idea how much of that water is being contained, how much of that water contains, or of that brine mixture, is containing the salt in terms of kilograms per liter. So we don't know that. So I'm just going to put a question mark here. We don't know that, but we know that we will be left with kilograms per liter, and we know that it's going to be draining at a rate of 15 liters per minute. Okay, well, let's keep going then. Let's actually go through and let's identify what it is that we're going to be looking for. Okay, so here we go. For this rate out, and I'll highlight it here, or you know what, I'll wait on the highlighting because I want to make sure I change that question mark. What I want here is I want to interpret this question mark. Now, the way to do this is we want to figure out how much of that water, or how much of that water contains the salt, or how much of that water brine mixture contains salt. Therefore, what I need to be looking at will be some function which we will be looking for, some function in terms of t. This function is going to be the amount of salt in kilograms after t minutes. All right. So there we are. That's what we're going to be looking for. Okay. So now that we've extracted this, and now that we know what it is that we're looking for, now we can go through the whole process and start piecing all of this together. All right, so let's go through and let's start identifying. Okay, so here we go. We do know the amount of water, the amount of salt in kilograms after t minutes. Well, that we don't know. That's y of t. All right, so that's my y of t. That goes here. we do know how many liters are in this tank. How many liters are in this tank? Well, in order to figure out how many liters there are in this tank, you're going to see that we don't need to figure that out at all, because there are 1,000 liters from the very beginning. I'll put a star here and I'll link it over here. There we go. Which means my amount of salt in kilograms will then need to be divided by 1,000, because we have 1,000 liters of pure water within that tank. So this is all of my rate out that I am observing. Oops. So this is my rate out. Great. All I have to do now is piece all this together. All right, so let's go ahead and start piecing this together. dy dt is going to equal to 0.05 multiplied by 5. This should naturally get us 0.25. Notice the unit of measurement here is going to be kilograms per minute, plus 0.04 times 10. This will then get us 0.4. So 0.4. And again, we're left with kilograms per minute, minus our last equation here. Well, we're going to have 15 divided by 1,000, and that's going to be 0.0015. Oops, sorry, one too many zeros. My apologies. 0.015. There we are. And this is y, because again, we're multiplying by that function of y. And again, this is going to be kilograms per minute. Okay, not looking too bad so far. All right, everything looks like it's looking pretty good. So we're going to keep going then. And what I'm going to do here is I'm now going to start adding these coefficients together, these like terms. I'm going to add them together. I'm going to add them together, and when I get my result, let's see, I get 0.25 plus 0.4. That's going to get me, oh, nice. I get 13 over, okay, so I actually get 0.65, so that's pretty good. So let's say dy dt is going to equal to 0.65 minus 0.015y, and this is going to be kilograms per minute. All right, everything's looking good so far. So let's go see if we can now try to manipulate this a little bit more. Now, I personally don't like integrating with decimals. I try to integrate with fractions if I can, because it makes things, to me, a little bit more easier. And if we take the fractions, well then, this actually turns out real nice to say that the rate of change, so my dy dt is going to be equal to 130 minus 3y, all divided by 200. And again, this is at a rate of kilograms per minute. Well, all we got to do is solve now. We need to solve this differential equation. So going through the whole process for this differential equation, well, let's see what we get here. All right, I'm going to multiply by dt. So multiplying by dt, I will get dy is equal to 130 minus 3y divided by 200 multiplied by dt. I'm going to omit the unit of measurement just for now. All right, so unit of measurement is being omitted for now. I'll bring it back into the mix in a bit. Okay, and then I'm going to divide by 130 minus 3y. So this will be 1 over 130 minus 3y, and this is dy. On the right-hand side, we're left with 1 over 200 dt, and we can integrate as such. And now, once we integrate, now is when we can go through and we can start extracting what we need. Okay, great. So on the right-hand side, well, that's still going to be 1 over 200, but now since we're integrating with respect to t, it'll be 1 over 200 multiplied by t plus some constant. On the left-hand side, you can do this with a u substitution. Okay, so I'm going to say u sub. If you make a u sub where u is equal to 130 minus 3y, then du is going to be negative 3 dy, and then you can proceed from there. So on the left-hand side, we're then left with negative 1/3 natural log of the absolute value of 130 minus 3y. All right, that's looking pretty good. All right, it's looking pretty good so far. Now, remember, as we did with the last problem, as soon as we were able to integrate and get y by itself, we were able to use that initial condition. Well, we want to use the same thing here, because again, we're trying to find how much salt is left in the tank after t minutes. So notice that the tank is going to contain 1,000 liters of pure water. Okay, so we got that in mind. Y of t is the amount of salt after t minutes, which means at t is equal to 0, meaning we haven't started, there are only 1,000 liters of water, pure water in there. So how much salt is within that water? None. So I'm going to say note, at t is equal to 0, there is no salt in the tank. Therefore, y at 0 is going to be 0. And extracting this initial condition now, we then get 1/3 multiplied by the natural log of the absolute value of 130 minus, in this case, 0, is equal to 1 over 200 multiplied by 0 plus c. Then we're going to be able to get the constant here. Well, the constant for c is going to be negative 1/3 multiplied by the natural log of 130. Nice. So now we have a constant. And now that we have a constant, we can go through and we can keep solving this. So I'm going to keep solving this now, and I'm going to bring the original equation. So let's bring that original equation that we were working with, and I will highlight that initial equation, or sorry, not initial, that equation that we are working with. Making sure I haven't used this color so far. Okay, pretty good so far. Okay, I'm going to use that down here. So that's negative 1/3 natural log of the absolute value of 130 minus 3y is equal to 1 over 200t. Remember, plus c is now this constant that we have as negative 1/3 natural log of 130. All right, and again, that was that equation that I was working with. Let's bring this down here. Boom. There we go. Okay, let's keep going. Let's keep solving for y. So I got to keep trying to solve for y in this case. I'm going to multiply by 3 onto both sides, and let's multiply by negative 3 onto both sides. Multiplying by negative 3 onto both sides now will get me 3 divided by 200t minus, or since we're multiplying by negative, make all these negatives, there we go. So it's going to be plus natural log of 130. It's looking pretty good so far. I like this. All right, let's keep going. We got to try to solve for y. that means we must be able to eliminate this natural log some way, somehow. So let's go ahead and let's do it. Taking the exponent of both sides, e to the power of natural log of the absolute value of 130 minus 3y is equal to e to the power of negative 3 over 200t plus natural log of 130. All right, not bad. Let's keep going. On the left-hand side, I now get the absolute value of 130 minus 3y is equal to e to the power of negative 3 divided by 200t plus natural log of 130. Okay, it's not looking too bad right now. Now, you're going to see here that at this point in time, we're left with the left-hand side being the absolute value and the right-hand side being equal to e to the power of negative 3 divided by 200t plus natural log of 130. However, the right-hand side will always be positive, because e to the power of any number never crosses the asymptote or horizontal asymptote at y is equal to 0. Therefore, it never attains any negative y values. Again, therefore, never goes below the x-axis. In other words, all of these values for e to the power of any variable, we're going to be left with positive values. So the left-hand side is just 130 minus 3y is equal to e to the power of negative 3 over 200t plus the natural log of 130. And we can keep solving for y. So as we keep solving for y, I'm going to go up here now. I now get e to the power, I get negative 3y is equal to e to the power of negative 3 over 200t plus the natural log of 130. All of this minus 130 divided by negative 3, which means y is negative 1/3 e to the power of negative 3 over 200t plus the natural log of 130 plus 130. And this is the function that we are looking at. All right. So again, the function looks kind of weird, but it's a really nice function that we get to work with. All right. So that's looking pretty good. So let's clean this up just a little bit more here. And I'm going to see if I can clean this up a different way. Let's see, if I take natural log here and then do e to that, then that'll be nice. Okay, so I think I want to clean this up just a little bit more. And where I'm going to do my cleaning up here, it's going to be right up here. All right, so I'm going to start cleaning that up. So what I'm going to have here is negative 3 over 200t plus the natural log of 130. Now this first term, what I'm going to do is I'm going to do the natural log of e to the power of negative 3 divided by 200t. Very, very similar to what we did in the previous section when we were applying L'Hopital's rule. So the reason I want to do this is because now I have the addition of two logarithms. And when we have the addition of two logarithms, well then naturally what we can do is we can multiply their arguments, which means I have the natural log of e, in this particular case, or let's say 130, times e to the power of negative 3 over 200t. And this piece here is that portion or that part that I wanted to clean up. Simply because now this portion, that highlighted portion, can now get substituted. And if I make that substitution, negative 1/3 e to that power, which is the natural log of 1/3 e to the power of negative 3 over 200 t plus 1/30. Then I have my inverse operations, e and natural log, and I can simplify this just a little bit further. Multiplied by 130 e to the power of negative 3 over 200 t plus 130. Wowzers. Wowzers indeed. Okay, so this is our answer for part A. Wow. Check that out. That's part A. So part A says how much salt is in the tank after t minutes. Well, the salt that is in the tank after t minutes is y. In this case, we could say y of t because y will be a function of t. So y of t is equal to, and we have negative here. Yep, that looks pretty good. So negative, oh, and I see a 130 here. So what I'll do is I'll factor out the 130 and the 1, so 130 divided by 3, and then I'll distribute that negative in. So it'll look like 1 minus e to the power of negative 3 over 200t. Wow, that's not too bad. The unit of measurement here, well, salt, as we saw before, we were given the rate. The rate was kilograms per minute. And if we integrate the rate, then we should naturally just be left with kilograms. So the salt after t, the amount of salt, cheese and crackers, the amount of salt. Okay, so the amount, the amount of salt after t minutes is y of t is equal to 130 divided by 3 multiplied by 1 minus e to the power of negative 3 divided by 200 times t, and this is going to be in kilograms. Whew, that is intense. That is intense. Now, let's see how much is going to be left after 1 hour. So let's keep going. So part B, after 1 hour. Well, that's not going to be too bad because now we have an equation. And remember, t was in minutes. So if t is in minutes, then we're going to be making our substitution of 1 hour is 60 minutes, which means we're going to be left with 130 divided by 3 multiplied by 1 minus e to the power of negative 3 divided by 200 multiplied by t, and in this case t was that 60, so multiplied by 60. There we are, just like that. And then our result should get us really close to an approximation of 25.7 kilograms. Wow. Success. So after 1 hour, there should be about 25.7 kilograms left of salt in that mixture. Now, one of the important aspects that you can see here is, well, how much saturation will we have? Is there a maximum saturation that is going to exist in this tank that we're constantly mixing the brine in? And the way you can check this is to take t and make it approach infinity. As t approaches infinity, e to the power of negative 3 over 200 times t, where t is getting large, because of the negative exponent, this overall exponential function will tend to 0. Which means, as t gets larger, as t goes to infinity, y of t will then approach 130 over 3. In other words, there is a maximum saturation level, and that maximum saturation level will be about 43.33333 repeating kilograms of salt. Interesting. So that is the whole process of separable differential equations. A lot of work that goes into these types of problems. Okay, so please make sure that you're giving them your best shot, and if you have any questions, please feel free to send me an email. All right, send me an email or stop by my office hours. So I hope you all enjoyed this lesson, and I hope you all enjoyed learning this lesson, and I will see you all for the next time. Till then.